sensitivity should be in that tab. Well, it's not uniform. Very not uniform.
Hey, you came back after all, even when you had the chance.
I'd say this density of light. So he really, like, usually it's like.
So welcome back to the second to last session of the day, where Kevin will continue and tell us about real applications. Kevin, thank you.
Thanks. Okay, so the kind of message of this next segment of the talk is to just reassure you that what I've been speaking about so far along hasn't been something kind of idiosyncratically special about uniform random 3-SAT, because after all, I think the real kind of promise of what I've been telling you about is that it's possible to understand rich, complex, realistic settings that we can't really get traction on theoretically. So I kind of made that claim to you, and then I turned around and started looking at the setting that arguably we can say the most possible about theoretically. So that might have seemed disappointing. I guess I did that because that's probably the single distribution of SAT that has gotten the most attention, and it's probably the place where our claims can most likely sort of feed theoretical work. So I think that's a good kind of test bed to begin with, but we certainly wouldn't want to end there. So at this point, I'm going to consider both SAT distributions that arise in practice and also problems other than SAT. So here's the kind of broad message that I have for you. Across the board, we've found that empirical hardness models work pretty consistently almost everywhere we've tried them. Over the years, we've looked at 4 different problem domains: combinatorial auction and winner determination, satisfiability, mixed integer programming, and traveling salesman problems. We've looked at dozens of different solvers, including each domain's best state-of-the-art solvers and various black box commercial solvers. And we looked at dozens of instance distributions, including the kind of third-party benchmarks that people test their solvers on, and various real-world data that we've been able to get our hands on, including domains like hardware verification, computational sustainability. We've also looked in detail at the underlying machine learning and tried to figure out which kinds of machine learning approaches are best for this problem. And at this point in the talk, I'm going to pivot from speaking about regression, which is sort of the easiest to think about, a ridge regression, which is a parametric model and is therefore relatively easy to think about, computationally easy, to random forests of regression trees, which is a bit of a sort of messier, non-parametric, but higher performing learning paradigm that we've typically found is the best thing to use. So I'm in this part of the talk going to go at a much higher level of detail and just give you a sense of what the results look like, because I'm particularly excited to talk to you about the applications part of the talk, and I don't want to steal too much of my own time. So here are some examples for satisfiability. So here I'm showing you hardware verification data from IBM, and Spear, which is a solver that is particularly well suited to hardware verification. Here I'm looking at the SAT competition, which is held every year. It's divided into 3 different tracks: random, handmade, and industrial kinds of data. And we just took everything and we threw it all together into one giant data set. The reason people don't do that is that the data is so different. The different solvers do well in different sets. So this is a particularly heterogeneous data set. And we looked at mini-SAT, which is a pretty good across-the-board SAT solver. And here on the left-hand side, I'm showing you linear regression on both of these data sets. And on the right-hand side, I'm showing you random forests. At this point, I've got root mean squared errors given here to the extent that you can interpret them. And you can just look at the pictures. And what I want you to take away from this is random forests really do seem to be doing a better job of making these predictions than linear regression is. But in both cases, we're able to do something reasonable. We're still getting somewhere. We're working with the same features in both cases. But particularly in this SAT competition case, where the data is really heterogeneous, we have very, very different kinds of instances in the distribution. This is pretty hard for a parametric linear model to work with, because what it does in one part of the instance space sort of ramifies over to what it does in another part of the space. And when things are really discontinuous, that's a problem. So a non-parametric discontinuous model like random forests can have stronger performance there. And you can see a pretty big qualitative difference between this figure and that figure over here.
Aiming to predict runtime versus whether it's SAT or non-SAT.
Yeah, so for the rest of the talk, I'll be speaking about just predicting runtime. Yeah.
Vertical thing on the right.
Sorry, what's the vertical?
Points on the right.
What's the? So this is predicted runtime, and this is actual runtime?
No, on the left hand.
On the picture.
Oh, you say what's going on there? Well, so we only ran the solver for a finite amount of time, right? So these are cases where the actual runtimes were truncated. We don't actually know what they were because we had to, these are exponentially varying things. We couldn't run it for like 6 years just to get the 1 point exactly right, So at some point we have to cut it off. That's a problem in the machine learning because this is what's called censored data, right? My true response value is censored. All I know about it is that it's at least that big. And it turns out there are machine learning methods for learning in an unbiased way from censored data. Actually comes from actuarial science. Actuaries look at a bunch of people and they want to predict when you're going to die. And it's very inconvenient for them that you're not dead yet. And all they know is that you're going to live at least as long as you have so far. So that amounts to this same kind of censorship. So they've developed techniques which we can use for the happier problem of predicting algorithm runtime. OK, so anyway, so much for SAT. Let me show you something similar for mixed integer programming problems. So behind each of these graphs means a grad student spent forever writing scripts and learning how to wrap the solvers. And we generated entirely new features for mixed integer programming. And we got our Cplex license working. And then all of these individual dots are runtimes on a cluster somewhere that we had to use 1,000 computers for like a month to generate all these points. So I can just throw this stuff around like it's nothing. But trust me, there's blood, sweat, and tears behind every one of these graphs. But so what again you see here for mixed integer programming is, again, linear regression is doing something not too bad. It's better with random forests. This is the best picture that I've ever seen. Here we have a root mean squared error of 0.02. And it's not because there's no variation. And indeed, when we have the same data set for linear regression, it's not like it's a trivial data set. But this is just one where random forest really nailed it. This is actually computational sustainability data from Cornell that's about habitat preservation for the red-crested woodpecker. So this means that we can, this doesn't mean we can predict habitat. It just means that we can predict whether or not we can protect habitat and whatever. But so all of this is just meant to say, here we're looking at Cplex. This is MIPLib, which is a crazy heterogeneous MIP data set. So again, this seems to work. And finally, here's traveling salesman problem. And there's less kind of available data and also fewer good solvers available for TSP. TSP seems to be a place where our features are less powerful. Honestly, we've spent less time thinking about TSP. But we don't really seem to have great features. We have kind of OK features for TSP. And I think this is what it looks like when you have sort of OK features. So we're still not doing bad. Our RMSEs are still under 1. But you can see, like now, random forests aren't doing that different from regression and linear regression anymore. There's a little bit more similar. But
what were your features in the TSP?
I don't remember. I have to look at the paper. I mean, like 80 different things that everything you might imagine about the TSP. I mean, we can look at it together if you're interested in TSP. But off the top of my head, I don't remember. But anyway, I mean, I guess the upshot of this is this really wasn't a story just about uniform data. This wasn't a story just about one solver. This wasn't a story about SAT. All of this stuff carries over to these really very different problems, and particularly to very different data sets that have real-world structure. They arose in some application. They're actually important for something. So then we can do various different investigations of kind of the way we build the models to try to understand more about what's necessary. One thing we can think about is how the model scales with the number of data points. So in these plots, I'm going to be plotting correlation coefficient between the true and predicted runtimes so that I can take an entire scatter plot and boil it down to one number, and then look at how those scatter plots change as I add more data. Correlation coefficient of 0 is really bad news, and 1 is perfect. So here, and I guess less than 0 means that you're anti-correlated. You're doing actually really pretty badly. So here you can see how ridge regression performs as we grow the number of training points on a log scale here. And you can see that once we get up to sort of thousands of data points, we're doing pretty well. Here, mini-sat on this heterogeneous SAT competition data. And here's random forests. So you can see both that they do better, which we already saw before in the large model, that they were doing better in this heterogeneous data, but also that they're much more efficient about data. So we're learning much more quickly. The error bars are coming from bootstrap replicates of different sub-data sets of the same size. And then here's some other models that we considered. It isn't like we only looked at these two. So we also looked at Gaussian processes, the projected process approximation of Gaussian processes. And we looked at regression trees. And they're falling in between these two methods. Looking at a different data set, here's CPLEX on a heterogeneous mix of benchmarks. And this is one where the linear regression does really pretty badly, ridge regression. So it's like flatlining for a while before it finally manages to get somewhere, still with a lot of variance. And in contrast, again, random forests are doing a lot better. So I think if one actually wanted to do this in practice, we're pretty confident that random forests are a good way to go. Incidentally, one reason random forests are good, for those of you who know something about this learning method, is they can never extrapolate. So they always, they're almost like a data structure that stores the data that they've seen. And so they do regression by returning kind of the mean of a set of points that lives at a leaf. And what that means is it's never possible for them to give a bigger value or a smaller value than they've ever seen before in the data. And that's one of the ways that these parametric methods really screw up. They can predict something wildly wrong. And so that just sort of naturally falls out of ridge regression, out of random forest, that it doesn't make that mistake. So far I've been talking about modeling single algorithms. Something that might be interesting to think about is parameterized families of algorithms. So imagine that I have various design choices that I might have made about my algorithm, like what's my restart probability? Or should I use pre-processing or not? Or should I do my variable branching by the most constrained variable or the most constraining variable? Or, I'm giving you examples that might be continuous or they might be discrete. If they're discrete, they might be ordinal or categorical. And some of them might be potentially conditional on the values of other parameters. So they might be things like, should I do random restarts at all? And if so, what should the random restart probability be? So we can define a set of algorithms by some parameterization like this. And just to have some terminology that I'll use, I'll call a fully instantiated algorithm that I can actually run that gives parameter values to everything a configuration of my solver. So now we can think about generalizing our models to these spaces of algorithm families. And here, we did a pretty exhaustive analysis in a paper, but here I'm showing you only the hardest case, which is where we trained on various training data as before, and then we tested on both instances and configurations that we'd never seen before. So we're asking about algorithms that we never ran before, based on other algorithms that are similar and instances that we never ran before. And notice that the problems get harder, our quality gets worse, but nevertheless, we're still able to often do not badly. So we're even able to reason across algorithms in a sort of limited way, not reasoning about algorithms that no human has ever crazily thought of before, but reasoning about algorithms within an infinite class of candidate algorithms. Looking again at scaling with the number of data points, we see something kind of similar here. That again, it's not too bad, and again, random forests are more efficient. Finally, we can kind of visualize how we perform in the joint space of instances and configurations. So here we looked at 1,000 randomly sampled configurations and 383 instances. And then we just evaluated on all of them. And here are the true runtimes given a trained model. So these are all new configurations and instances we hadn't trained on before. And then here's the true runtime where we just sorted this by average hardness so that the picture kind of looks clean. And so you can see kind of the landscape for this problem that there's some instances where dark is easy. I think, let me make sure that's right. Yeah, so dark is fast. So there's some instances that are easy for all configurations, and there's some instances that are hard for all configurations, and there's a lot of instances in the middle where it really matters what algorithm configuration you choose. Sometimes it's going to be fast, and sometimes it's going to be slow. And you can see there's kind of a structure to it. There's sort of a shape that this thing takes on. And so, right. And so then here is our predicted runtime using the random forest. And I guess I just want you to notice that more than just kind of getting a summary statistic like root mean squared error or something right, we're really capturing some of the structure of this landscape with the model prediction. If we look at other models, this is regression trees. This is the projected process, approximate Gaussian processes. And this is ridge regression. So you see, they're all sort of doing something, but it's a lot less accurate. You get a sort of finer grained sense of how the differences are. Here's random forests again. And finally, I guess here again, I'm showing you random forests. Now I want to say, what if we trained only on 100 data points? Here's how it degrades back to the original one. And here's if we looked at only the one most important feature and the one most important parameter. And you see that so instance feature, we characterized the instances using only one feature, and we allowed the model only to care about variation in one parameter, even though there was variation in all of the parameters in the test data. And you see we're actually able to capture a lot of the structure there. So this tells us that sort of the high order story here on this particular data set of SPEAR for software verification is captured in this low dimensional way. So that's all I want to say about that, but I just want to give you some sense of our ability to visualize this and sort of give you some kind of visual picture about it. But now I want to move over to applications. So now I want to kind of ask, and as you can see, we've done a lot of different things in this sort of space of applications. I want to ask, so much for beyond worst case complexity, just sort of answering these philosophical questions about what makes algorithms hard. In a more kind of practical way, what can we use, what can we benefit from knowing that it's possible to predict something about how long an algorithm will take to run? In what ways can that change our design of algorithms in practice? First of all, let me remind you of Moore's law, because it's always nice when you look at a practical computer science talk to see a graph of Moore's law. Here it is. And it's important in particular to remember that this cyan line here is the rate of growth in clock speeds over years on the x-axis here. It's a graph from The Economist just from a few months ago. And what you can see is that ever since sort of early 2000s, the computer on your desk has not been getting any faster. Right? The clock speeds on individual chips have pretty much flatlined for reasons that have to do with physics. Like there's a problem with heat, and there's a problem with the speed of light, and there's only so much that you can do about these things. But what they have been able to do is get much more parallel and get much lower power. Which means that we can still pack more and more transistors on a chip. So the number of transistors on a chip has been marching along, according to Moore's law, unabated, even as we've had this sort of lived experience of computers not really getting much faster. Now this was, full disclosure, this was from an article about how Moore's law is going to end. There's sort of a Moore's law about every year there will be twice as many articles about how Moore's law is going to end any time now. So any day now. But at least in the recent past, there's been this steady increase in semiconductors on chips. And what that means is, as much as we might have kind of forgotten about it, things that algorithmic approaches that might have seemed really stupid not that long ago are starting to become feasible. We can really do absolutely crazy approaches of just throwing insane amounts of computation at a problem that would have been prohibitively dumb not very long ago because of this exponential growth. And I argue that's what deep learning is all about. So deep learning, let me give you sort of as optimistic a view of deep learning as I think it's possible to give. Right? So the classical approach said, let me come up with features based on expert insight. Let me go to NIPS and understand deeply what's the fashionable machine learning model du jour. Let me learn how to use that. Let me manually tune hyperparameters in some clever way, and I'll build a machine learning algorithm that works well. Right, so the deep learning approach says, let me take machine learning models from the 80s that are extremely highly parameterized, just neural networks with gazillions of parameters. Let me use expert knowledge very little just to identify appropriate invariances and model biases, like maybe convolution is going to be important in images, things like that. And make it deep in the sense that I have many, many layers of nodes being things that carry parameters, each depending on the previous ones. Then let me take tons and tons of data, plus a few clever ideas about regularization to avoid overfitting. And then let me fit these models by doing absolutely ridiculous amounts of computation using graphics cards. So let me just essentially take old ideas, lots of data, and super fast computers, and I can build amazing machine learning models. That's pretty much the story of deep learning. So I argue that we should think in optimization along similar lines. And for lack of a better name, I'm going to call this deep optimization. So the classical approach is to say, let's turn to an expert to design a heuristic algorithm, and let's iteratively conduct small experiments to figure out how to make our design better. And keep iterating until the conference deadline gets close, and at that point, terminate, send the paper off to the conference. If it gets rejected, then repeat. The deep optimization approach basically mirrors what we saw with deep learning. So let's take a very highly parameterized algorithm to express a combinatorial space of heuristic choices that an expert might think makes sense. So let's use expert knowledge only to identify parameters that might make sense in isolation. And let's make this deep in the sense that there can be many layers of parameters with each parameter depending on the previous ones. Let's take, again, lots of data to characterize a distribution of interest. And let's computationally search this space of many algorithms instead of relying on some notion of human insight. So let's think about algorithm design, at least in the heuristic sense, as being performed by gigantic scale simulation by these tons of cores that we have lying around, rather than thinking that we have deep insight about how these heuristics combinatorially interact with each other. So I'm going to call this kind of core building block that we're going to need algorithm configuration. And so the input that we're going to be given is some algorithm which is parameterized by every design choice that some human expert thought might possibly make sense. And it's going to be deep in the sense that we have many layers of parameters depending on parameters. If I have multiple algorithms that I've kind of thought of, that's a high-level parameter which says which algorithm do I use, and its own parameters depend on that, and so on.
So
yeah.
A deep optimization algorithm that you mentioned are just essentially genetics algorithm. They are doing exactly this type of thing. If you give them a lot of power, they are just doing essentially some kind of genetics algorithm, local search essentially. And at the end they will get
well, why don't you wait to hear the methods that I'm going to propose? But in fact, people have used genetic algorithms as a way of building algorithm configurators. Not the best methods around, but they do work.
They work. I have seen in practice, and they work actually.
Yeah. So I with some co-authors, co-authored a local search algorithm configurator called ParamILS, which is not genetic, but it's based on local search, and it's pretty good. There's something else called GGA, which is Gender Genetic Algorithm, which is an algorithm configurator. It's less good, but also competitive. So definitely this exists. I want to tell you about another approach called Bayesian optimization, which is not local search at all, and which depends on these kind of modeling ideas that we've been talking about. So let me build to that. But broadly speaking, this whole kind of vision of deep optimization, sure, there's nothing telling you can't use a genetic algorithm to do this thing. Just as ultimately deep learning is about gradient descent, right? I mean, not necessarily saying these things have to be super tricky. But so what we want to do is solve the stochastic optimization problem of finding a parameter configuration that has good performance. Why is it stochastic? Because we're looking only at a sample from the instances, and the algorithms themselves can be randomized. And this is a black box function optimization problem because we want to do this optimization without reasoning about how the algorithm works. We're just going to evaluate the algorithm at a given point, and then we're going to observe a runtime from the algorithm. And what we want to minimize is some performance measure that cares about runtime, let's say average runtime. This makes this a really interesting black box function optimization because you have these crazy design dimensions. They're not all continuous. you have this extra dimension of which instance do I test, which you could always do it at random, but there might be smarter things to do. You might want to do a blocked experiment design. You might start to notice that some instance is always hard, and so maybe you're unlikely to learn something from it. The cost of gathering a point is not constant. The points that you're looking for are fast, and the fast points are really cheap to observe. So there's this sort of virtuous cycle that if you're doing well, it's not costing you much. But if you look at a bad part of the space, it could cost you a ton to observe how bad it is. But you don't have to run it to completion. You can choose to terminate it early. That's a censored sample. But then you've learned less. All you've learned is that it's worse than whatever threshold you pick. And so you have this other design dimension about how much to censor. The reason I belabor this is I think this is a really exciting problem in stochastic optimization. And I know that stochastic optimization is one of the putative themes of the semester. So I want to put this up as this other sense in which this work kind of interfaces with the algorithms and uncertainty theme here. And I want to sort of plant this seed for you guys. But the best current methods for solving this problem are based on the fact that it's possible to make these runtime predictions. So let me tell you a little bit how these methods work. So there's this methodology called sequential model-based optimization that goes back to work in the late 70s. It's a popular method for thinking about black box function optimization. Mostly it's being used for entirely continuous functions that don't have most of the complications that I told you about in the last slide. Here's sort of a cartoon of how they work. So what I do is I observe my function at a variety of different points to begin with. I do some kind of initial experiment design. And then I fit a model to those points that predicts for every value of my parameters what happens. So that's what this solid line is. This is my model prediction. And this dotted line is my true objective. So in this particular cartoon that I'm drawing here, there's no noise. Whenever I observe at a point, I get the accurate value, but then I can be wrong in other places. And here in this cartoon, I'm fitting a Gaussian process model, which is what's typically done in this literature. And what's cool about that, what makes this Bayesian optimization, is that I get uncertainty estimates from the model. So the model is pretty sure that it's right close to points that it's observed before, and it gets pretty uncertain as it gets far away from points that it's observed before. Then we have an acquisition function that says, how good is it going to be to look at a point in a particular place? And that cares both about how high the predicted function is in this place and how much variation there is, because it knows that there's not much to be gained in these points that have very small error bars, for example.
Using Gaussian processes?
For these cartoons, I am. We've experimented with them. We again use random forests, but they make less pretty pictures because they're piecewise constant. And so I think the intuitions are nicer from Gaussian processes. And so then the acquisition function is maximized at this point. So we look at the acquisition function everywhere, which we have kind of offline access to. But that's not a black box. We maximize the acquisition function. We actually get a new data point, and then we refit our model to the new data point. And that gives us a new acquisition function. And then we keep doing this. And eventually, we get to figure out where our function is minimized without looking at it everywhere. And so this is a pretty promising approach. And notice that what makes it work is that you've got the ability to make predictions across your parameter space, which is what the first part of the talk was basically about, the fact that we can do this when it comes to heuristic algorithms. In the spirit of the talks that came before, let me also notice that there's a whole bunch of work on regret bounds for these SMBO methods, and something I'm interested in talking with people about later. Here's a little animation to show you a simulation of how this actually looks. Maybe you could get it from the previous picture, but I think it's nice to sort of see it happening in a moving picture. So this line here is our fit model. The dotted lines here are the error bars around the model. Again, we're noiseless. The blue line is the true function, which we only get to observe at the points that we look at. The red line is the point that we're looking at. And here's our acquisition function here, which is expected improvement. So we're asking, on expectation, given that the point I'm looking at is better than the current minimum that we've seen elsewhere, how much better is it? And we're going to go look at the place that is predicted to have the highest expected improvement. So let's watch this thing go. I think. Try that again. OK, I think it's going now. And so see how the error bars start tightening up. The acquisition function is jumping around. And the model doesn't end up being correct everywhere. It's still pretty wrong out here in the edges. But after a while, the acquisition function is still maximized around here, and so it ends up just kind of looking around this minimum. I think it's about to just restart. I'll let it run one more time so you can just see how this works. Of course, we're doing this in a high-dimensional space. This is looking at one parameter, and we're looking at maybe hundreds of parameters, not all of which are continuous. But intuitively, this is kind of how these methods work. So they're really kind of fundamentally driven by the ability to make accurate predictions about runtime. So the method that we've, the non-local search method that my collaborators and I have come up with that I think at this point is kind of indisputably the best algorithm configuration method out there is called Sequential Model-Based Algorithm Configuration, or SMAC. Basically works more or less the way that I described. It works with random forest models. So it learns a random forest model kind of as we just saw before in this joint space of instances and parameters. So the fact that we can generalize to new instances and parameters is very important. We then marginalize out the instance features to get expected performance. We find a parameter value that maximizes some acquisition function, in this case expected improvement over our previous incumbent. We actually go out and do an algorithm run, see what happens, do an incremental update of the model, and we just keep iterating until we run out of time. So this is a really powerful way of finding new algorithms from some known space of algorithms that perform well. And we've released this as open source code that anyone can download and use. And it's been really widely used, both in industry and by other academics, both by us and by a whole bunch of other people. If any of you have a kind of practical frame of mind, this is something that you can download and get working. It's really not that hard to use. And kind of the sky's the limit for what it's good for. It's being used for problems as varied as just grinding away on competitions, to scheduling exams at UBC, to improving the performance of computer Go or protein folding, or even making machine learning algorithms work better. So it's a pretty general approach. Yeah.
So when you say it's won the SAT competition, in what category? What exactly is it won?
I'm trying to remember exactly what's happened in SAT with it, but people have tuned other people's algorithms in ways that have caused them to then win, right? So it isn't like we've designed the algorithm ourselves, right? We're given the starting point. So I'm trying to remember exactly what it is about the SAT competition that led me to put that up there. I'd have to remember. And actually, it's partly complicated by what I'm going to tell you on the next slide, which also touches on the SAT competition. So let me tell you about that, which is. Well, maybe somebody else has something they want to say before I dodge that question. Is there anything else on algorithm configuration? Yeah.
Does this do both hyperparameter optimization as well as algorithm selection simultaneously, or?
Yes. And actually, we've also extended this to a problem in machine learning that I didn't mention here. We built a package called AutoWeka that uses this same approach to solve the problem of model selection and hyperparameter optimization at the same time. So, if you are a sort of machine learning novice, you download the Weka package, which is basically one piece of code that runs every machine learning algorithm in the world. It can be configured to be every machine learning algorithm that anyone's ever heard of, just about. You don't really know where to begin. So we've built something that is integrated into Weka. You can download it from the Weka package manager, and you basically hit a button that says start, and it just starts trying things. And uses SMAC to reason about which machine learning methods in Weka work well, and ends up finding for you both a model family and a hyperparameter setting for that model family that give you good performance.
What prior do you put internally on the space of hyperparameters and algorithms?
I think we start with a uniform prior on just kind of ranges that made sense to us. I should mention that under the hood, dealing with overfitting is very important there, as it is really in the algorithm case. It's possible to overfit in algorithm design just as it is in machine learning. It's really a machine learning problem. So a lot of what it takes to make SMAC actually work properly is to do with sort of significance testing, like making sure that we're not becoming falsely confident that some incumbent is better. Yeah.
So just to understand, if I have, for example, a scheduling and resource allocation, so if I have some problem that I want to solve, so do you need like an input different algorithms, or what? It's fine.
So typically,
what does it do?
So what it does is you have to give it an algorithm that you want to run that has many parameters. You might, in your case, use Cplex, which I think we actually give you a wrapper for Cplex. So we say Cplex has, last count, I think 63 parameters that don't affect numerical precision, but affect just the strategy used by Cplex. So give me a distribution of input problems that have to do with your scheduling domain. Give me Cplex and this Cplex wrapper that knows what its parameters are, and I'm going to figure out an instantiation of Cplex that is optimized to work well for your problem. That's what it does. The thing is, turns out there's lots of stuff in the Cplex design space that's really good for one problem that isn't good overall. So it isn't the thing that Cplex exposed as the default. So I think we did a collaboration with Cplex at one point where we actually started seeing 10,000 times speedups on some of the client problems that they gave us, which they weren't terribly surprised by because they weren't trying to do point-wise the best thing. They were trying to do well on average with their default settings. But there really is a lot of scope for improvement by doing this kind of thing. But even if we did this perfectly, as Tim alluded to in his talk, it's not necessarily going to be the case that a single algorithm is going to be the best thing to run on every instance in a distribution. We've pretty robustly observed that there's no kind of best SAT solver, at least yet. What we find is that different solvers work well on different subparts of the distribution. And these performance differences can be pretty enormous. And so there's another way that we can see something we can do from empirical hardness models. If I have the ability to make accurate runtime predictions about how long a solver is going to take to run, then given some new problem instance I've never seen before, I can run a model for every one of my solvers, see how long they're likely to run, and then run whichever one is predicted to be fastest. If the runtime differences are big, that can be a really big win. That can end up, I can end up with the min of runtimes across the solvers rather than the min of the averages. And that can be just a lot better. So we have been in the SAT competition for years, entering something called SATzilla, which is graphically depicted here at a SAT competition in Tokyo. SATzilla does exactly this. We take other people's SAT solvers and we sort of put them together, knowing kind of nothing about how they work inside, but just learning models of them, and we're able to dramatically outperform other people's SAT solvers. So in fact, we do something more complicated than what I just told you about empirical hardness models. So we've elaborated SATzilla quite a lot over the years, so it can work with randomized and incomplete algorithms. It reasons about running pre-solvers for a short fixed time before eventually picking something. We optimize for scoring functions other than runtime. And we do all of this in an automatic way where we make decisions about all of this. We can think about all of these questions of should I have a pre-solver, how long should it run for, as other parameters that we can think about, again, using this kind of deep optimization approach. And if you think about it for more than a minute, you'll notice that algorithm selection really isn't a regression problem anymore. What I really care about is selecting among a finite set of alternatives. This sounds like classification. Now, the cost of a classification error depends on the runtimes, which is why the runtime thing still makes sense. So using just kind of regular ordinal classification is a bad idea here. But cost-sensitive classification is a thing in machine learning, and that makes sense because it might very possibly be that the runtimes are a complicated concept to learn, but the decision boundary, the cost-sensitive decision boundary between different solvers, which one should I pick, is a much simpler concept to learn. So we've had more success using cost-sensitive classification. And if you've got lots of cores, you don't even need to do that. You don't need to do selection at all. You can just run many things in parallel, and whichever one finishes first, so much the better for you. SATzilla has taken the SAT world by storm. In 2003, we did kind of a bad job as a proof of concept, and we came second and third in a bunch of categories. Then I got some grad students. I got a job. And so we entered the 2007, 2009 SAT competitions, and we won firsts in a lot of categories, and everyone got very upset. In the 2012 SAT challenge, we were eligible to enter 4 categories, and we placed first, second, with like dozens of entrants in every category. And then the SAT competition people became so upset, they changed the rules to say that we couldn't enter SAT competitions anymore. And so this story ended. But I think it ended with us having proven our point that this is a good thing to do. So I think people in the SAT community are no longer really in doubt that algorithm portfolios are an effective approach.
How to technically you paint? I have an algorithm that runs with it.
Well, I mean, the thing is, it's academia. It's like they say don't do this thing, and it's exactly the thing that I did. Then it's bad behavior.
But I mean, do you take the algorithms from that same year that are?
No, we can't do that. But every previous year, they have to make them open source. So we're always, otherwise it would almost be a foregone conclusion that we would win. But it's essentially our ability to select among people's last year ideas versus whatever progress they made in the next year. We were. And of course, it's possible that the selection is working badly, that we make bad selections, and it would have been better to just stick with one thing, but typically not. And also the instance distributions change arbitrarily, adversarially from year to year. They might be trying to trip us up, so the training data is not necessarily IID anymore. But nevertheless, we were doing okay until they shut us down. And I think the overall message of the story is this was a pretty robust approach. And so I was kind of happy almost that they banned us because we get to stop doing it. It was a lot of work every year. We sort of made our point. And I think something that's kind of cool about it is there were a lot of solvers that people had decided just sort of sucked. Like they were really just washing out in the competition. And we were really bringing them back because we discovered that for like 5% of instances, your solver is amazing. And the rest of the time, it's terrible. But we can predict when it's going to be amazing and use it only there. And all of a sudden, it's a really great thing. Whereas there was this sort of herding behavior in the SAT community where everyone cared about average performance. So they were all doing relatively similar things. And I think there's something sort of nice about the fact that we're bringing back these kind of uncorrelated ideas. Again, there's open source software out there. You can use it for problems other than SAT. So far, what I've told you about assumes that we start with some manageable set of relatively uncorrelated solvers. You might, if I really want to tie a ribbon around this deep optimization idea, let's say all I start with is a huge deep parameter space where maybe the top level parameter is which solver among many solver families do I use, and then each of them has their own crazy space. Let's say I want something that works completely automatically, but that will produce a portfolio of as uncorrelated as possible solvers as its end result. This is something that we call Hydra. We built an approach that does this. And basically, it greedily builds up a portfolio one solver at a time by running configuration at each stage. And the way it works is that we change the objective function from one stage to the next. So it turns out that SMAC doesn't care what objective function you give it. So we can change, on the second round, we take an idea from economics and think about marginal contribution. So we say, when I'm adding a second thing to my first solver, I'm going to score it not according to its own runtime, but I'm going to score it according to the minimum of its runtime and the runtime of the other solver. And so anything it does better, it gets credit for. Anything it does worse, I'm just going to use the other solver anyway, so I don't care how badly it does. But all of its competitors are able to get that same runtime too. And so then I'm asking kind of how much are you improving average performance through this kind of iterative improvement. This is a submodular objective function, so so greedy optimization makes sense here. This ends up working pretty well. So I'm almost out of time, but let me finally get to the $88 billion number that Amos waved in front of you like a red flag at the beginning of the talk, because we put all of these ideas together in the work that we did for the FCC on the incentive auction. So actually, the projected profits are more like 30 billion. 88 billion is just one of the input numbers to this whole thing, but it's probably as little as 30 billion in the end of the day. But yeah, the way this is going to work is that the federal government is buying back from television stations their right to broadcast. They're going to end up buying out roughly half of the television stations in the United States. They're going to take that spectrum and resell it to cell phone companies that want to use it for more modern purposes. And they're going to take everybody else who either they didn't choose to buy from or who refused to sell, and they're going to change what frequencies they're operating on so that they're operating on some sub-range of the frequencies, so they get something clean to sell. And this repacking problem of deciding, so baked into the auction, there's a question of, is it possible for me to offer a lower price to some guy And in order to decide that, I need to decide, is it possible for me to put him back on the air with this reduced band of spectrum and with all the other people that are already on the air right now? And without getting too much into the details, that's a graph coloring problem with about 3,000 nodes in the graph, about 20 colors, maybe 15 colors, and about 3 million constraints between all of the different stations on the scale of the whole United States. And so every time I want to think about a price movement of one of the 3,000 stations, every single time the price increments for one guy, I need to solve an NP-complete problem. And if I fail to do it right, if I want to solve one of these problems, but I don't manage to solve it, then I'm leaving money on the table. The starting prices are something like $10 million. And when my first decision of can I go from $10 million to $8 million, that depends on whether I'm able to find a solution to a satisfiability problem, a satisfiability encoding of a graph coloring problem. And if I fail, that means it just cost me $2 million for that one problem. This is real. And our software is actually running right now for the FCC. So this was a huge project that involved many people. Let me just shout out particularly to Neil Newman, my PhD student, and Alexandre Fréchette, my former PhD student who ran off to Google. Hi, Alex. Many others, a couple of economists from Stanford, Paul Milgram and Elia Segal, were kind of instrumental in this, as well as Holger and Frank helped to drive some of this work, as I mentioned before, and various people at the FCC. So we gathered a bunch of data over the past year using simulations at the FCC and varying all kinds of simulation assumptions, which never mind what all these things mean, but varying all kinds of questions about how big was the auction going to be, who's going to participate, how much are they going to value it. And we generated about 1.5 million instances from many auction simulations. And what we wanted was to be able to solve all of these NP-complete problems within 1 minute, because we have to do them sequentially. So one round of the auction is grinding through 3,000 stations, and we can get about 2 rounds a day. So just from what the client is willing to put up with. So given the variation in runtimes and so on, we figured that we really can't run any problem for more than about a minute. So the question was, how well can we do in a minute? When we started, people were thinking about mixed integer programming solvers. And so again, we have training data and test data. Everything that involved fitting something, we use the training data. What I'm showing you here uses the test data. So on the x-axis here, this is runtime from 10 to the minus 2 seconds up to 1 minute here on a log scale. And here's the fraction of instances in our test set that we were able to solve within each amount of time. So what you would most like to see is a graph that goes straight up and then stays there. Right? It's a cumulative density function. That would mean that I solved everything within like less than a second. And what you're seeing here is that these two state-of-the-art commercial MIP solvers are solving, in one case, about 10%, in one case, about 1/4 of the instances within a minute. And that's terrible. That means that doesn't mean that we would get 25% of the stations right. That means we would get 25% of the price movements, many of which we would never get to because we would have had to stop earlier. As soon as we had an unsolved problem, that station is done forever. So you couldn't run the auction with a solver like this. This would be way, way not good enough. We looked at SAT solvers. They hadn't been thinking about SAT. And SAT solvers are a lot better. So we have the SAT competition. We have all these different SAT solvers. We tried everything. And they're doing a lot better. Our best thing, a local search solver called DCCA, is getting about 2/3 of the instances solved. That's better, but still 2/3 of the price movements is not enough to run an auction. So then we started using the application ideas I told you about today, these various deep optimization ideas. So the first thing we looked at is we took all of these solvers and we tried to optimize them using SMAC. And I'm showing you here only the best one. But here's the solver that used to be best. Here's the solver CLASP, which is a SAT solver from a team in Germany that is particularly well suited to deep optimization because it has many, many, many parameters. And here's CLASP after configuration. And just notice how it now becomes by far the best thing, way better than it used to be. Still not good enough to run an auction with. Now we're at about 3/4 of the instances. So then we used Hydra. So then we continued doing this configuration to build a portfolio of many different SAT solvers with a variety of different heuristic ideas that we added ourselves, which we just exposed as more parameters. And this is kind of our punchline. we ended up with a portfolio of 8 different solvers, and the performance, which is this red line here, we're now solving something like 98% of the instances within a minute. And this is what the FCC is actually running in the auction. And it makes a real difference, because if every time we fail to solve a problem, we're really causing the US government to not collect money for kind of no reason except computational complexity. So I think this is a good kind of practical example of the fact that these techniques really work in practice. So I'll leave it there, and thanks to all of you for your attention.
We have time for more questions.
So you talked about using the prediction of runtime to pick whichever one would give you the shortest runtime. And I'm wondering if, like every SAT heuristic needs to both be able to say when there's a satisfying instance and prove when there's not. And I'm wondering if you designed 2 separate things, one that was good for proving satisfiability and one that was good for proving that something is unsatisfiable, and then using your prediction of whether or not something is satisfiable, how you would do that. Have you looked at that?
That's a good idea. So actually, we did something sort of like that here. Maybe I turned this off already. We did something sort of like that here. You'll notice if I look at the names of the solvers, we actually have a portfolio of 2 algorithm families, Satinstein, which I didn't tell you what it is, but it's basically a family of local search solvers that we built ourselves that sort of, the sort of convex combination of every local search SAT idea anybody ever had in one code base, so that you can sort of stitch them together and make crazy new local search solvers. Local search is particularly well suited to this because the ideas sort of compose pretty easily. And so all of these Satinstein solvers are local search, which means they can't prove unsat. So they really are optimized for satisfiability. I didn't tell you this either, but it turns out in this auction domain, most of the problems are satisfiable, because most of the time you're making price movements where once I encounter a guy that causes an unsatisfiable problem, I freeze his price forever and I don't see him in any more of the problems. So there's a tendency to kind of hit one unsat problem and then kind of veer away from that part of the space. So we spend most of our time with satisfiable instances, which is why these guys predominate. We do have a couple of complete solvers which allow us to prove unsat. So in that sense, we're doing something sort of like you said. Something more explicit like what you proposed might make sense, except we had so little unsat data here that wouldn't have gained us much in this application. But in another one, that might matter. Yeah?
Why stop at problems in NP? So there are lots of important P-space hard problems that people have worked on heuristics for ages on. So does your framework need, for example, succinct certificates, or what is?
Not at all. No, I mean, we don't have succinct certificates with unsat problems, for example, anyway, right? Really what we need is runtime variation. So if you have problems where every problem in the distribution takes pretty much the same amount of time to run, there's very little to be gained. I'm not saying that's going to be true for every problem in P-space. I'm just saying that's really the thing that means that you're going to gain something with these approaches. Otherwise, I think it's just kind of an accident of the sorts of problems that, in my day job, I'm a kind of game theory person. We just run into a lot of these sort of NP-complete discrete optimization problems in thinking about game theory. So I've been sort of naturally focused on those problems. But there's really nothing to make us think about that. People have used it. People have extended some of this stuff even to like sorting problems, for example. There's like certain choices about sorting algorithms where you can get not exponential variation in runtimes, but still sort of meaningful variation in runtimes, and you can make selection choices there. People have shown that you can even do something in those sorts of settings. So I don't think that was a big win, but that shows that you're certainly not limited to NP-complete problems. All right, thanks everybody.
I believe